Here we go, another Lewis dot diagram, in this case for carbon dioxide. And we know the system pretty well, but there's a couple of newer things I want to introduce in this one. So here we got carbon dioxide, carbon and oxygen, and you know the drill already. Here we go. What are the number of valence electrons? Carbon 4, oxygen 6 that you probably memorized by now. A total of 16, double check. Yep, 4, 6 times 2, 12. You don't want to be wrong on this, so it's worth a double check. And then we're going to put our little bonds between the carbon and the oxygens. That uses up 4, so you've got 12 remaining, and we know where those go. They always go on the surrounding atoms. You never put them on the center first. You always do the surrounding atoms first. Otherwise, you're going to run into some problems. So follow that rule. So let's get them there. And there they are. Voila. 6 and 6. We took those 12 remaining electrons and distributed them beautifully around our surrounding atoms, but there aren't any electrons remaining right now. So we've got a problem with our carbon, because our oxygens have, here we've got 8 are low potential energy, the best configuration for these, but carbon, it's got room for 2 more electrons, and it's got an attraction, so if we pull those electrons in, we'll have a better energy configuration, a lower potential energy. The things roll downhill. So let's see. What are we going to do? Well, the system will take one of these pairs of electrons from the oxygen, the surrounding atoms, and bring them here, so the carbon can end up having them shared. It's a second shared pair of electrons, and now our carbon has 6 pairs of electrons, 2 shared. All of them are shared. And we just need another couple of electrons. Now, you're not going to take the other electrons from this oxygen. It's already shared a pair, and it's better to end up using these. There's less stress. The oxygen is not going to be dragging them as much. So there we go. Now we've got our oxygen with its 2, 4, 6, 8 4 pairs of electrons. This oxygen has the same. And now our carbon, with these 2 extras being shared, will end up having 8 also. So we're in good shape for this. So let's now go to examine what we end up having here. We have our first bond, which is referred to as our sigma bonds, and we have 2 sigma bonds, and then we have 2 pi bonds. But the next critical thing is determining the number of domains. And let me just get this so we can see the entire molecule here. There we are. We deal with our center atom again, and we see that there are 4 things, but we never include the pi bonds in our domain count. That's a common mistake. So forget the pi bonds. Don't use them in your count. There are only 2 domains, 2 things that take up space around our carbon atom. And that's going to be critical for the shape of the molecule. So our steric number is only going to be 2. Even though it's a pretty complicated molecule in that we've got 2 sigmas and 2 pi's, when we count the domains, the things that are hovering around our carbon, we end up using just a steric number of 2. So don't forget that. That's a common error. And if you do, you're going to run into problems on the shapes of molecules. Okay, let's go to the next model here. We've been talking about Lewis dot diagrams, which are very, very easy and fast to do. 4 minutes, and we've got the CO2, and I was dawdling at part of it. I'm sure you could have done it in 2 minutes. But it has a weak spot in that it shows this second bond in both cases as being identical to the first. It doesn't really differentiate between sigmas and pi's. The atomic orbital model, which deals with s and p orbitals, is more accurate here. But of course, look at the drawings I've got to make. I mean, they're wretched. The second bond, the pi bond, really is a set of p orbitals, and they in effect have arch over and underneath these atoms. And here you can see the diagram that's involved. And the consequence of this is that in terms of rotation, which becomes important in shapes of molecules, when you get a pi bond, you cannot rotate independently as you can with a sigma bond. And that'll show up later. Now, another interesting model is the molecular orbital model that you need computers for. And I thought I'd just bring that up because this is sort of a drawing of it. And they talk about electron densities. And here, let me flip over to a diagram of what they would use for showing what carbon dioxide is like. We've got our carbon in the center, and here you can see the two oxygens which are rotating around. And these diagrams show the densities and the arrangements of the electrons around the carbon dioxide. Very neat model, but you've got to deal with a computer to be able to do it. Of course, the molecular oral model is not going to be used in AP Chem, and we'll talk more about hybridization and atomic orbitals in the next chapter. Okay, that's carbon dioxide, and we'll close down.